So let's start. So this is about sustainable homes and business premises. It's essentially about whole building thermal retrofits. And I'll spend most of my time talking about that. But in planning this webinar, Marianne and I also discussed matters such as water usage, accessibility to buildings as part of sustainability, the costs of doing a whole building thermal retrofit, and what statutory approvals you might need. The topic strictly is sustainable homes and business premises. Buildings are usually divided into residential premises and non-residential premises, which is where business premises come in. But it raises the question, what's a building? Next slide, please. Okay, so the usual definition that you'll hear spoken about in the architectural world is that the building is a climate modifying enclosure. None of this building is some beautiful object in the landscape. A building is a climate modifying enclosure. A building should keep its occupants dry when it's wet outside, it should keep them warm when it's cold outside, and it should keep them cool when the weather is hot. The design approach that focuses on making buildings goes beyond just keeping occupants dry, which seeks to advance their well-being, is called sustainable design. And thank you for that. Sustainable design is obviously about sustainability, and sustainability is about maintaining our environment, economic and social well-being long into the future. It's about satisfying our current needs without compromising our ability to meet future needs. Next slide, please. So sustainability is about achieving comfort, because we all want to be comfortable in our buildings, by using the resources we have to hand, which is space, materials, energy, water. We want to do that more carefully, more efficiently, and so more sparingly than perhaps we have done in the past. Any detriment to the environment when we're doing this should be minimized. And it is the case that a damaged environment can be improved by good sustainable design and construction. A million people might not believe me, but that's the case. And hopefully this evening I can demonstrate that where our building environments are damaged, we can make them good. Next slide. So the context for this, of course, is climate change. The economist Paul Samuelson credited John Maynard Keynes as having once retorted, "When my information changes, I alter my conclusions. What do you do, sir?" The climate is changing, so will we now change our buildings? The colourful pattern on the screen are the climate stripes for Northamptonshire. On my screen, the images of people sort of covers the right hand of that. I don't know if I can move that, but I think you get the impression, get the picture that obviously it's getting hotter. Just how warm it could get was exemplified last week, when just up the road it was 40.3 degrees Celsius. But really, climate change is not just about global warming, it's about extreme weather, as Texas found out in early 2021 when it froze basically during winter. So in changing our buildings, we should consider that climate modifying properties in both cold weather and in hot weather. But with the English heating season being about 9 months long, believe it or not, preparing for cold weather is really our main concern today, and that's what I'll concentrate on. Next slide, please. So there are about 23 million dwellings in England. About 4.7 million of those predate the end of the First World War. houses such as Marion and I live in. And just under 10 million of those, so nearly half, predate the end of the Second World War. The thermal image to the right tells a story. The blue colors are cold bits of the building. The red and yellow bits are the hot bits of the building. And you can see that most of that building is hot. The British housing stock is the oldest and most ill-suited to modern climate modifying expectations in Western Europe. So where to begin modifying a building? Well, the normal engineering approach is to address the most significant defect first, but the normal business approach is to go for quick wins. Well, the primary defect is clearly heat loss through the surface elements of the building, as that image shows. Next slide, please. This is a fairly typical summary of where the heat goes. About 25% of it goes up through the roof, about 35% of it goes out through the walls, about 25% goes through doors and windows, and about 15% goes through the ground floor. Those are nominal percentages, and from house to house that will vary. Obviously, if you live in a bungalow, the roof represents a much larger part of the surface area than if you live in a mid-terrace house. But what is noticeable about that diagram is that there is more heat going out through the walls than there is through the roof, despite everybody being encouraged to do loft insulation first. Next slide, please. There are three modes of heat transfer, and we need to know how heat is transferred in order to know what to fix in our buildings. So the three modes of heat transfer are conduction, convection, and radiation. I hope you can all remember this from your school days. Conduction is characterized by a material property which is called conductivity. Conductivity is how well a material conducts heat. Heat always travels from hot to cold, just as water always travels from high to low, always goes down the hill. When two materials are in contact, the heat will travel from the warmer material to the colder material until they're both in equilibrium. Like water always trying to find the easiest path down a hill, heat will always try to find the easiest path of least resistance through materials. And so the path that the heat takes isn't necessarily always the path that you expect it to take. The second mode is convection, and that is when heat is carried through a fluid. That fluid could be water, like in your central heating system, or the fluid could be air. I know it's confusing to call air a fluid, but technically that's what it is. And the diagram shows some cold air passing over a warm surface, being warmed up, and then rising because warm air rises. And that certainly happens on the outside of buildings, but equally air passes through the elements, the surface elements of a building, through gaps and cracks and leakages of all kinds. And as it does, it carries heat with it as well. The third mechanism is radiation. You're all familiar with radiators from your central heating system. They get hot, they radiate to anything that is cooler than it in the room, which is usually almost everything, including people, given the temperature that radiating panels get to. But the building radiates as well. It radiates to its surroundings. Typically, the outside will be colder than the building. And at nighttime, the sky is quite cold as well. And the building will radiate to the sky as well as to the physical surroundings. Next slide, please. So we want to do a whole building retrofit, and this is best done holistically rather than piecemeal. By that, I mean that you should have a comprehensive and consistent solution to what you want to do, but that doesn't mean you have to do everything at once. You can, of course, phase the works, partly because works are disruptive and partly because you might not have the money to do everything that you want to do in the first instance. But in saying that, you need to sequence the work appropriately. Otherwise, you'll find that you are doing things like destroying finished surfaces that you've just created and so on. And that is known as scrap and rework, and you want to eliminate scrap and rework as possible, much as possible. The slide should say scrap and rework, it doesn't, sorry. Now, a building is an active system of interactive parts and processes. It appears to be just something of a masonry lump in the landscape, but that's not the case. And we need to consider those processes when we attempt a whole building retrofit. Otherwise, we may come up with unforeseen circumstances that are definitely not what we wanted. Next slide, please. So this diagram just shows some of the interactions to do with the building. In the triangle, we have on the edges building fabric, building services and people and how they interact. But on the outer circle, there are things like thermal transmission, thermal mass, I'll explain later, air tightness, the site, the location of the building, the shape of the building, the orientation of the building, what energy supply we have, how efficient and controllable our systems are. And also, as far as people are concerned, lifestyle, do you work from home, do you go out to work, behavior and habits, all these things interact. The diagram just shows dotted arrows between some of them, but the reality is that everything interacts. Next slide, please. So a building is a complex system. Modifying one part of that system is almost certainly going to impact other parts of the system. So I can't tell you that improving the thermal performance of a building is a straightforward thing to do. It's not. Next slide, please. So buildings are for people for the most part, and the occupants' thermal experience of the building is going to be as a set of interactions with the building and the microclimate inside the building. So the diagram is showing things like air movement, air temperature, humidity, the temperature of the surfaces in the room. Remember, heat always radiates from hot to cold. If a person in the room is warmer than the surfaces in the room, then that person will radiate heat to the surfaces. I've heard people call that cold radiation. Of course, it's always hot radiation, but it's an unpleasant feeling. The activities of the person, if you're sitting watching telly, then you're not generating much warmth yourself. If you're up and doing the ironing, then you will be metabolizing more and you'll be generating more heat. Thermal comfort depends on the modes of heat transfer that I've just said, especially convection and radiation as air moves around the body. All those factors can be influenced by modifying the building in ways that thermal comfort is improved. Next slide, please. And really that's the point of this evening. We start by defining the goal of the retrofit. It might sound trite, but that's what you've got to do. Is the goal to generate zero carbon dioxide emissions in the use of the building? Or is it to make a presently uncomfortable building thermally comfortable all year round? Or is it simply to knock a couple of £100 off the fuel bill? Those are quite different goals and would require quite different building modifications to be achieved. To be simplistic, turning down the thermostat and dressing as if you were on a trek across Antarctica might solve the third option of knocking a couple of £100 off the fuel bill. But wearing that much clothing might make going about the activities of everyday living somewhat difficult. Replacing all your gas appliances with electric ones and then sourcing renewables only electricity tariffs would satisfy the first option of zero carbon dioxide emissions. But if you didn't reduce your energy demands, then you would probably face bankruptcy. Electricity is about 4 times per kilowatt hour. The price of electricity per kilowatt hour is about 4 times that of gas. And given the price of both of them right now, that's not really a way to go. Obviously, any retrofit that you want to undertake has to have a budget. You have to be able to afford what you're going to do. You might also have to deal with planning constraints, and you will certainly have to deal with the building regulations. But taking all those things into account is just good risk management in any project. Next slide, please. So the diagram is a conventional energy hierarchy diagram saying where to start and where to progress. So we start by just being more efficient, switch off things we don't need. Obviously, you can't switch off your fridge freezer, everything would melt. But there are other things that you might have on that you don't need. Like I've got another computer running at the moment that I'm not using. Then we can look to being more energy efficient, purchase better appliances, look for lower energy losses. Then we can think about renewables, sustainable energy on site, or getting our electricity from suppliers that only sell renewable electricity or electricity from renewable sources. If we were more than just a house, we might look to carbon capture, obviously not really feasible at a domestic scale. And as a last resort, look for carbon offset, although I think we are becoming increasingly skeptical about carbon offset. In last year's California fires, one of the forests that was burned, reduced to cinders, was actually had actually been sold as carbon offsetting, so that didn't work very well. Before one undertakes a retrofit project, it's worth finding out what is possible without modifying the building, and part of that would be to make sure the building is itself well maintained before undertaking any particular further work on the building. So retrofitting a building, we want to define a goal of the retrofit project, and that is necessary, but it's not sufficient. What actions do we need to take to meet the goal needs to be identified and their sequencing planned. It may require more than just having a look at the building. It may require that a relevant professional is instructed to perform calculations that give a baseline for what the building is currently like, so you can plan what level of improvement you want to achieve. And I've got some funny stuff right at the end, at least I think it's funny, about that. For residential buildings, that might mean simply doing U-value calculations, and I'll describe what a U-value calculation is later on, right through to a full-blown standard assessment procedure, SAP analysis. If you've bought or sold a house in the past 20 years, you've probably come across an EPC for the house that would have been arrived at by doing a reduced SAP analysis. Generally, though, in retrofitting, we take a fabric first approach to thermal improvements. Next slide, please. So we want to improve the fabric of the building before we upgrade any building services, but then we want to look at upgrading building services. Obviously, the big thing at the moment is moving from gas boilers to heat pumps, but there may be other things we want to do too. And the third step would be to think about installing renewable energy generation on site and energy storage through some kind of battery system. Next, please. We might also consider, if we're ripping the place apart, installing water capture and reuse equipment. We might also want to address accessibility to the building, unless we plan to move when we get old. And we might also consider using landscape to modify the microclimate around the building. And lastly, we shouldn't forget non-thermal aspects of the building, things like daylighting, quantity of daylighting, quality of daylighting in the building, and acoustics, the sound insulation that the envelope of the building provides. Next slide, please. Right. So heat escapes through the building through conduction, convection, and radiation, reducing the building envelope's ability to conduct heat will reduce heat loss through conduction. It also will mean that the external surfaces of the envelope are cooler, and so there will be less heat lost by radiation to the environment. And making the building more airtight will reduce heat losses by convection. If we're going to reduce heat by conduction, we do so by introducing insulation. Now, Jonathan gave a talk about insulation some weeks ago, so I'm not going to deal with this in great detail, but one can classify insulation materials into groups. The columns are things which are fibrous. They say things like rock wool, glass wool, cellulose, which is made from recycled newspapers, sheep's wool, cotton, which can be made from recycled clothing, and flax. Cellular insulants, an insulating material is called an insulant. Things like cellular glass, which comes in blocks, that's recycled glass, vermiculite, rigid polyurethane, which comes in boards. You can buy those, I think, at B&Q. Phenolic insulation. My screen keeps going to sleep. Expanded polystyrene and extruded polystyrene, all those things, as it says on the diagram, are derived from oil. And cork. You can also buy sheets of cork as insulators, and obviously that's plant-based. I should have mentioned that rock wool and glass wool, recycled glass and vermiculite are come from materials. The process of manufacturing some of these insulants, particularly rock wool, is inherently energy intensive. So for example, rock wool is called rock wool because that's exactly what it is. You superheat rock and you draw off fibers from the rock. Now you can imagine the amount of heating you need to be able to do that. So that's quite energy intensive to make. Other materials, other insulants, such as the polystyrene insulants, expanded polystyrene and extruded polystyrene, they are blown, and by blown I mean blown in the sense of blowing bubbles. You blow a gas through the material as you're creating it, and it puts bubbles in the material, and that's why it's a good insulator. But those gases can themselves be global warming gases. So next slide, please. So we often talk about the global warming potential of insulants, and you might be able to read that diagram, but basically the diagram shows a measure of global warming potential for a range of insulants. Obviously, things like wood fiber have very low global warming potential because they just come from trees. Whereas something like polystyrene, extruded polystyrene, has quite a high global warming potential. Right at the end, VIP, I've not mentioned yet, is vacuum insulated, vacuum insulation panels, which is quite a specialist product. And I'll briefly mention that, but later on, but not something that is commonly used in houses. So generally one wants a GWP of less than 5. So most of those insulants do have a GWP of less than 5, some of them considerably less than 5. Next slide, please. Right, so as I said earlier, conductivity, which is measured in watts per meter Kelvin, is a property of a material. Kelvin, in case you can't remember your school physics, a 1 degree interval of Kelvin is the same size as a 1 degree interval in Celsius. But whereas the Celsius scale starts at the freezing point of water, so 0 degrees, water freezes, Kelvin starts at absolute zero, which is minus 273 degrees Celsius. So the freezing point of water is 273 Kelvin. Also, we tend to say degrees Celsius, but we don't say degrees Kelvin, although people do tend to slip into that. So conductivity is a property of a material. Conductance is a property of an element made from that material, and it's going to depend on the thickness of the material. The inverse of conductance is resistance. So I've got two equations and they're very simple. So the resistance is the thickness divided by the conductivity. Clearly, as the conductivity gets smaller, the resistance will get bigger for a particular thickness. So next slide, please. An example of rock wool, its conductivity is 0.037 watts per meter Kelvin. If we have 100 millimeters of rock wool as cavity insulation in a masonry wall, then it would have a resistance of 2.7, and the measure is Kelvin per watt. Next slide, please. Now, the wall that I showed was made of a number of layers, not just the insulation. And that is characterized by a U value. Building regs specify a maximum U value for walls. U value is measured in watts per square meter Kelvin. So that's per square meter of wall surface. And the conductivity of all the layers has to be considered. So we had brickwork, then the rock wall, and then the blockwork, and then some gyprock paneling. We need to work out, we need to find out their conductivities and then work out their R values. And then we work out the U value as the sum of the reciprocal of those R values. So we add all the R values together and we divide it into one. Now, clearly, if R is a big number, then U is going to be a small number. And in general, we want U values to be as small as we can make them. According to the building regs, if a project, if you're going to do a retrofit project, then the walls must achieve a U value of 0.18 watts per square meter Kelvin. By the way, I have absolutely no idea why they're called U values. R values are called R values because of resistance. I have no idea why U values are called U values, but they are. Americans, of course, tend to think that bigger is better rather than smaller is better. So they like to talk in terms of R values rather than U values. But in this country, the building regs talk in terms of U values. Now, to do all that, you need to know the conductivities of the materials that you have in an element of the building. Next slide, please. And manufacturers will always advertise the thermal conductivities of their insulants. And as I said before, the smaller the number, the better. So the best commonly used insulant is aerogel with a thermal conductivity of 0.014. Most of the insulants cluster around somewhere between 0.2 and 0.4. Some of the more natural materials have higher conductivities. In other words, they're not so good as insulators. Hempcrete and straw, straw in the sense of straw bales, have much higher insulants. What that means is you have to have a much greater thickness of those insulants in order to achieve the U values that you want. So if you're working in a tight space, you need to go for the better performing insulation materials. Next slide, please. Another property of materials is their ability to store heat. And that ability is called thermal capacity. Thermal capacity is also referred to as thermal mass, and in the construction world is more usually called thermal mass. Physicists probably don't like that. Tended materials tend to have greater capacity to store heat. So concrete, brick have a greater capacity to store heat than do things like timber. Actually, the thing that has the greatest capacity to store heat is water, but we can't really make buildings out of water unless we're Eskimos, and then the water's got to be frozen. So materials that have greater capacity to store heat are said to have a larger thermal mass. And the ability to store heat allows those materials to act as a buffer as the temperature changes. So we expose the material to some source of heat and it will warm up, but the speed at which it warms up, it warms to touch, it will depend on its thermal mass. So a thermal lightweight material like timber will warm up more quickly than a thermally heavyweight material, thermally massive material like concrete or brick. So they don't warm up to touch as quickly, but they're storing that heat. And what that means is that once the material is warmer than the environment that it's in, then the heat begins to leave that material. Now, a thermally massive material can store lots of heat, and so it can gradually release that heat into the environment. So if you have a brick building, it can store lots of heat, and then when it gets cold inside, then it will release that heat. You might have noticed last week that your building, assuming most of you live in brick buildings, your building got hot, and just when the heat wave stopped on Tuesday, it didn't mean that Wednesday your building went cold again. It took a day or two for the building to cool down. That's because it had stored the heat and was releasing it slowly. So in that way, it buffers temperature changes. Next slide, please. Now, we can put the insulation is the yellow stuff. I'm moving my cursor around. You can't see me move my cursor. The yellow stuff on that diagram is insulation, and you can see that you can put it in the middle, thank you, in the middle of a cavity wall. You can put it interstitially in between floors of a building or the ceiling and the roof. You can line the underside of a roof with insulation, and if you have a solid wall, as I have solid walls, you can either put the insulation on the outside of the material or on the inside of the material. Depending on where you put the insulation will affect the behavior of that thermal mass. So if you put the insulation on the outside, then you're insulating the thermal mass from whatever's the temperature is on the outside. If it's cold outside, that might be a good thing. If it's warm outside, then you're cutting off that source of heat. If you put the insulation on the inside, then the brick or the stone is exposed to the outside temperatures, and if it's cold outside, then the wall stays cold because it's insulated from the heat on the inside. If it's hot outside, that the wall heats up, but that heat doesn't pass through to the inside. Where you have exposed thermal mass, then it takes a bit longer for the surfaces of the room to reach a temperature where you're not radiating heat to it, or not too much heat to it. Whereas if you put insulation on the inside of that wall, then the surface of the insulant will warm up quickly, and so the room is said to be more responsive. That matters depending on how the building is going to be occupied. If you occupy the building intermittently, like you go out to work, so you wake up, you're in the house for an hour or two, and then you go to work, you're out of the house for 8 or 9 hours, and then you come back for a few hours before you go to bed. That's intermittent usage. Intermittent heating is better when the surfaces of the rooms are more responsive. If, like me, you work from home, then you want the temperature consistent throughout the day, and so exposed thermal mass without the insulation on the inside is preferable. As a general rule, where we have cavity walls, we put the insulation into the cavity. You could also put insulation outside or inside the wall, but interstitially is where it normally goes. If you have a solid wall, best practice is to put the insulation on the outside of the wall. Next slide, please. Doors and windows obviously are routes for heat loss, especially if they're poorly fitted, drafty windows, like the window in the room that I'm in now. A double glazed window has a U value of about 1.2 watts per square meter Kelvin. A triple glazed window has a U value of between 0.6 and 0.8 watts per square meter Kelvin. Now compare that with what the building regs require your wall to achieve, which was 0.18. You can see that these U values are much higher. And remember, big U values are bad U values. So walls, windows and doors, I haven't given transmission conductivities for doors, but obviously doors conduct heat too. These are much greater than for a well-insulated wall. Should we then make windows smaller so that we are losing less heat if we make them a smaller fraction of a wall. Well, the problem with doing that is twofold, well, threefold perhaps. One is that you lose the opportunity for sun coming through the window and warming the room, which if you have a south-facing room in winter, you're probably aware that on sunny days, the room can get quite toasty from the solar radiation. You also lose the opportunity of having good daylight in the room. The better the daylight, the less you need to use artificial lighting. And there's also a psychological benefit of having windows and having views out to the outside environment. So the smaller your windows, the less view you get, the less psychologically satisfying that window is. So it's a compromise. Design is always about a compromise. Big windows, lots of heat loss. The small windows, other problems. When we insulate walls, we need to be aware of how we deal with windows and doors. Next slide, please. So doors and windows have reveals, and they have lintels, and windows have sills. So the bottom left diagram is a horizontal section. So you're looking down on a slice through an insulated wall. So the brown hatched rectangle represents brickwork. The rectangles that have wiggly lines in them, the horizontal one and the vertical one next to it, they are insulation. So you can see that the gray bit to the left of the wall, that's meant to be the window frame. So you can see that that's the reveal where you have a opening in the wall for the window to go in. And if you didn't insulate that reveal, then the heat would find a nice little shortcut through the reveal to the outside world. So what you need to do to make sure you do is to insulate that that reveal. There are a couple of buildings in our area, one just a few doors down from Marion's house and another around the road, corner in Chester Road, which have had external insulation put on them, but they didn't insulate the reveals. And that the problem with that is that you then get an area of the wall that is cold, colder than other parts of the wall, which can be problematic. Clearly, if you put a lot of insulation into reveal, you'd actually start covering up the window. So that's when a highly efficient insulant is preferred. The image to the right with the shiny stuff in it, that's a retrofit where they chose to use vacuum insulating panels. What a vacuum insulating panel is basically a material a bit like a crate or some other open weave material wrapped in a foil, which is then evacuated. All the air is sucked out of it, and that vacuum then is highly efficient. To give you some idea, aerogel, which was the best that I listed in that table I gave earlier, was 0.014. A VIP is 0.007, so twice as efficient as aerogel. The reason we don't use vacuum insulated panels in houses very often is twofold. One is they're only guaranteed for 20 years. So what do you do after that? They may continue to work, we don't know. And the other is that as soon as you put a nail through them, they cease to work at all. So putting them behind plasterboard is probably not a good idea. But in this case, they put some material on top of it that wasn't going to be easily penetrated by somebody sticking drawing pins through. The other thing to notice in that photograph is the blue tape that's all over the place. They've used those tapes to tape the panels together and also to tape the panels to the other elements of the building. And this is to stop air leakage. It's 5 past. I'll carry on just for a few more minutes and then we can have a break. Next slide, please. Moisture. People underestimate moisture. Water really damages the fabric of buildings. And a common cause of damp in buildings is condensation, which is water in liquid form. Condensation forms when water vapor comes into contact with a cold surface. Obviously, if you have a nice cold drink in a glass on a hot, humid day, you tend to get condensation on the glass. The glass is cold. The humid air contacts with the glass, and the water vapor condenses into liquid water. There's always some amount of water vapor in the air, even when it doesn't particularly feel humid. There's always a degree of water vapor in the air. Next slide, please. Our buildings tend to have a lot of water vapor in the air because we do things like boil kettles, run showers, and in fact, exhale. Can't really be in a building alive and not exhale. All those mean that the atmosphere in buildings is quite humid. Most traditional buildings, and I expect most of you live in traditional buildings, are made of materials that are permeable to water vapor. We say that they breathe. So when you hear somebody talking about a material that breathes, they mean that it's permeable to water vapor. As the water vapor travels through the structure from the inside to outside, the temperature of the water vapor will cool, assuming we're talking about it being warm inside and cold outside. And that diagram's actually back to front. But never mind. As the water cools, it may cool to a point where it condenses into liquid water. That point is called the dew point. The dew point will depend on the temperature and humidity of the environment. But typically, if it's 21 degrees inside your house and on a winter's day, 60 degrees outside, then as the water vapor crosses the wall, it's likely to meet the dew point and will condense into liquid water. That is known as interstitial condensation. Next slide, please. Condensation can lead to mildew or mold growing. If you have timber parts of the structure, as in your roof, for example, it can cause the timbers to rot. And also if the condensation gets into permeable insulation material like rock wool, it can reduce the efficiency of the insulator. So we really don't want that to happen. In the past, buildings have relied on ventilation to take the water away. So our buildings were very leaky, and all that air movement helped carry the water away. But and roofs in particular were designed to be ventilating so that the timbers didn't rot. But when you pass air over insulation, it reduces the efficiency of the insulating material. That's known as wind wash, and it's actually taken into account in U-value calculations these days. So nowadays, instead of having leaky buildings, we install a vapor control layer to manage the movement of water through the structure. There are other names you'll hear for a vapor control membrane, vapor control layer. Some people call them a vapor check. Some people call them a vapor permeable membrane, or a vapor retarder, or a vapor diffusion retarder, or a vapor diffusion membrane. Most people call them a VCL. Sometimes you'll hear people call them a vapor barrier, but that's generally not a good term for it, because a vapor barrier is actually an impervious moisture barrier, such as a polythene sheeting that you might put underneath a concrete slab. So a VCL will reduce the amount of water vapor that passes through a structure, but it won't stop it completely. And there's a reason for that, is that water vapor passes through a structure both from the inside to the outside and the outside to the inside, depending on the relative environments inside and outside the building. So you don't want to stop water completely, because on one side of the barrier, you would get a buildup of condensation. So you need to allow water to pass through, and that's why VCLs do have a degree of permeability. There are other alternatives to VCLs. You can use timber board. OSB, oriented strand board, is most commonly used for that, or plasters can be used. Next slide, please. Right. This might be a good place to take a break, because it'll take me a few minutes to talk about air tightness.
Are there any questions with anyone before we start again? I can't hear anything, and I can't see any hands. Oh, there's one up. Julie's got a hand up.
Well, I did actually put it on the chat. I've heard that rock wall, cavity wall insulation loses its efficiency over time. Is that correct?
No, it's quite inert. So as long as it's kept in good condition, it's fine. The question is it in good condition? There are two things. One is, when you're installing it, make sure that you don't get any mortar dags or whatever dropping down onto the insulation, because that would reduce its insulation. It'll reduce the insulation. I won't go into the detail. Sadly, some building inspectors insist that there be a cavity between the insulation and one of the leaves of the brick of the masonry wall, and then you get, because they're concerned about condensation, but the trouble is you then get that air movement over the insulation, which is problematic. But yeah, if the material suffers condensation, then you'll reduce the efficiency. But otherwise, it's an inert material. It won't change.
Okay, that's good. How would you know if it deteriorated, if it had got condensation when it's between the walls? Ours was put in 25 years ago, you know, as part of the where they drill a hole in the wall and just.
That won't be rock wool, though.
No, it won't, will it? It's some sort of.
That'll be polystyrene bubbles.
Right.
No, expanded polystyrene bubbles. They blow the polystyrene bubbles into the cavity. Again, polystyrene is pretty inert. I suppose, being a plastic, it might degenerate over time, but I think that would mostly degenerates due to sunlight. You won't get much sunlight inside the cavity. So I think you're probably fairly safe. The problems with that process is generally how well spread the bubbles were. If you end up with little holes, air gaps in the bubbles, then you can get cold points on the wall. If you've not suffered any damp patches on the wall, then probably the bubbles were installed okay.
Okay, thank you.
Anything else?
Over to you then, Greg.
Okay, so carrying on, the next thing I want to talk about was air tightness. I've said that moisture vapor can be carried through the fabric of the building by escaping through, by air escaping through cracks and gaps in structures, and we don't want that to happen. Also, warm air escaping through the building envelope is just heat loss, and we don't want to allow those kinds of heat loss. The better that a building is insulated, the greater the impact of air leakage on the heat loss, because obviously we're not losing it by conduction. So most of what we're losing is we're losing through air leakage. Air leakage is called infiltration. So we're losing it through infiltration. It's reducing the performance of the building envelope, and we don't want that to happen. In winter, heat will escape from the inside to outside. Obviously, in a heat wave, you'll get heat coming from the outside into the building that you would rather be cool. So it can reduce the comfort of the occupants, and if the building is really drafty, it can also affect the health of the occupants. So we want our building to be draft proofed. Now, the comfort of occupants is dependent not only on room temperature, which is what all our thermostats measure and what people mostly talk about, but it's also dependent on air speed. And the diagram to the right is taken from a technical document, kind of thing that air conditioning engineers might look at. But basically what it shows is that comfort is dependent on airspeed and air temperature. And the point at which we might feel comfortable is, it's also dependent on air turbulence, but I don't want to get too much into the detail, but the point of the temperature at which we might feel comfortable depends on the airspeed. So with an airspeed of 0.2 meters per second, we might want a temperature of 26 degrees in order to feel comfortable. But at an airspeed of 0.15 meters per second, we might want an air temperature of only 22 degrees to feel comfortable. So the less air movement we have in a room, the lower the temperature needs to be to feel comfortable. So that means turning the thermostat down, which obviously is an energy saving thing to do. So basically, draft-free rooms can be comfortable at lower temperatures, and we can reduce our heating demand. Next slide, please.
Oops.
Thanks. So in order to achieve air tightness, we've got to seal up all the gaps in the building envelope. Excuse me. Air infiltration can happen in several ways, or a couple of ways. We can get structural leaks, which are basically gaps and cracks in the building fabric. We tend to get gaps around things like windows and doors, around loft hatches, but also around things like downlights. If you've got your downlights cut into the plastered ceiling, plasterboard ceiling, the floor is, the ceiling is probably ventilated to keep the timber structure dry, and so you can get leakage around there, separating floors, and so on. You can also get leakage where you have building services, so where pipes, cables, vents, and other stuff penetrate the external envelope of the building. So where your gas pipe comes in, where your water pipes come in, where your cables come in, where your broadband cable comes in. All these are brought into the building by making holes in the envelope of the building, and that can lead to air leakage. And if you're really unlucky, you can get both structural and service leaks in the building envelope. And these are things that you need to take account of. Next slide, please. In a retrofit project, the more airtight the envelope, the greater the need to have moisture control to stop the condensation and to ensure that the building fabric can breathe. So we can achieve air tightness by wrapping the building, basically. You can use an appropriate VCL. Some VCLs act as air tightness barriers as well. Or you can use timber panels like OSB or plywood or plaster. Traditional plaster on brickwork is actually very airtight. And you also need to, where you have things like timber panels or VCL sheets, you need to make sure that they're all sealed up. Or if you have dry lining plasterboard instead of wet plaster, then you need to tape up all the joints or stick them down, some way seal up the joints so that you don't get leakage between those things that are supposed to be stopping the infiltration. All that needs really to be part of the planning for the retrofit. You need to decide how you're going to control air tightness, and you need to decide the sequence of operations. So ventilation, once you seal up a building really, really airtight, then you have to deal with how you're going to ventilate the building. How are you going to change the air in the building so that it doesn't become stale? And basically, you can do that through mechanical ventilation or some form of natural ventilation. Part F of the building regs deals with ventilation, and there is a revised version of Part F which deals with retrofit. I said that Part L had introduced a requirement for U values for retrofit. Now Part F has a requirement for ventilation for retrofit. And basically it says that whatever the level of ventilation in a building was before you started the retrofit, the ventilation must not be made any worse by the retrofit. So you should get the same amount of air coming into the building as ventilation before and after the retrofit. If you can't do that, then you're going to have to, as part of the retrofit, take into account the need for ventilation. The guidelines recommend windows with trickle vents. Somebody in the relevant government department loves trickle vents in their windows. It comes up all over the place. The problem with trickle vents is they're immediately a hole in your air tightness barrier. So yes, they provide ventilation, but they also undermine your air tightness controls. Where you have a really, really airtight building, then you require mechanical ventilation. And that was briefly mentioned when we were talking about building services, in particular mechanical ventilation with heat recovery, which is a whole building form of ventilation. Next slide, please. Mary? Oh, good. Also, you may find your building control inspector insists that the retrofit project satisfy the provisions for the provisions of Part F for fresh air supply and purge ventilation as if it were a new build, even though it's only a retrofit. Building control inspectors can say, yes, but you're doing so much work, this is a new build. And so you have to satisfy that. Supply air for the dwelling then can be achieved either through continuous supply fans, in other words, mechanical ventilation like MVHR, or through background ventilators, which is typically trickle vents in windows. And Part F goes into how much background ventilator opening you have to have given the size of rooms and stuff like that, which you'll be pleased to know I did not put in this presentation. But if you come to do a retrofit and you do a lot of air tightness, then this becomes an issue. The building inspector might also require you to satisfy the purge ventilation requirements. Purge ventilation is when you flush the stale air out of a building by, if you like, throwing the doors and windows open, the kind of thing you would do at night after a very hot day. And again, Part F has requirements for the size of openings that you would need in order to satisfy purge ventilation. There is also a new Part O of the building regs which deals with overheating, and its requirements for purge ventilation are actually even more strict than Part F. So you not only have to satisfy Part F, but you also have to satisfy Part O of the building regs. Next slide, please. Right. Mostly been talking about the building almost out of context, but of course buildings exist in a particular context, and we talk about the microclimate around a building. So these are aspects of the building such as which way it faces, and so its exposure to wind, to rain, and to the sun, and these provide opportunities for thermal improvement, but they also may provide things that you have to address in doing your retrofit. So the diagram shows that you might get rain on the building, and that will obviously wet the exterior of the building, which might cause condensation inside the elements of the building, particularly if it's wind-driven rain. The internal environment interacts with the external environment, so you get somebody cooking, you get increased humidity, and so if it's quite sunny outside, then the vapor pressure will be lower outside, and you'll be drawing vapor from the inside through the fabric of the building to the outside, and so on. As I said, there's a whole complex system of effects going on, but if we take those into account, we can use them to our advantage. Next slide, please. So a trivial one is if you have a south-facing wall, you might want to put a sun trap on the south-facing wall, which in this country tends to be a conservatory, or depending on how posh you are, you might call it a winter garden or an orangery. That can trap the solar radiation, warm the wall that's behind the conservatory. It can also warm the air in the conservatory, which can be allowed to leak into the building as kind of preheated air. Obviously, in summer, then that conservatory may become a problem, and you have to work out how you're going to control the solar gain in that conservatory. Next slide, please. You could also use landscaping to good effect. So, for example, trees and hedges can be used as windbreaks if you're in an exposed environment. Maybe you live in a farmhouse or something. Also, they can provide shading. Obviously, deciduous trees have leaf in summer and go bare in winter, so you can get winter sun through the tree onto the building, which is useful, and then the tree leaves in the spring, and that provides shading for the building. The use of trees and hedges as windbreaks can also be problematic. Obviously, if you want a breeze on a summer's day and you've put a windbreak in the way, then that's not a good thing. So the landscaping has to be done judiciously. Planting right up close to the house. For example, bushes can be useful. They create a pocket of still air, which means that you don't lose heat from the building surfaces in winter by convection, because the bushes, if they're evergreen bushes, create this pocket of still air. They can also provide a degree of shading in summer, but of course, as I said, if it's an evergreen, then it's also going to block winter sunshine. So you need to make your choices which you prefer to have. But basically, we can use landscape to mitigate the detrimental effects of the climate. Next slide, please. I haven't really said much about building services because Darlene McCulloch dealt with that a few weeks ago in great detail. I put up this diagram, though it comes from a report that the Department of Business, Energy and Industrial Strategies sponsored the British Standards Institute to produce. And it's a matrix of what building services do and don't go with each other. So the red blobs show interactions which don't work. I'm using my cursor again, not helpful. The yellow blobs are caution, and the green blobs are interactions that are okay. So I don't expect you to be able to read this, but basically you can't just pull any old building services off the shelf. I come back to, this is a complex system. Some things work together, some things don't. Next slide, please. Now, installing services can disrupt newly installed insulation, air tightness membranes, and vapor control layers. So you can imagine you've done your wall, you've insulated it, you've got your vapor control layer, and then you've taped up everything, and the plumber comes and sticks a pipe through it. That's not a good thing. So you need to figure out how you phase the work so that you don't end up with these problems of completed work being having to be redone. Basically, in principle, you should install your building services before things like insulation and VCL, so that you can then tape around where pipes pass through those layers. And either that or just budget for the fact that you're going to have to redo work. But you need to take into account that some services will only be usable once, for example, insulation and other layers are installed. So for example, if you have a low temperature heating system, perhaps underfloor heating powered by a heat pump, then you can't use that until the building is well insulated. So maybe those two things have to be done in a single phase, and you can't leave them for a year or two before you do them, unless, as I said, you're prepared to pay for scrap and rework. Next slide, please. All right, water usage, not really a carbon issue, but it is a sustainability issue. There are two aspects to water usage. One is to reduce water demand, and the other is to recycle water. So next slide, please. If, as part of your retrofit, you're going to replace appliances which use water, so washing machines, dishwashers, possibly replace your bathroom and your kitchen, so toilets, baths, and taps and showers, then you should opt for low demand appliances or low flow fittings and install those. And in fact, if the building control inspector decides that this is a substantial piece of work and you need to follow the new build regs, you will have to install those anyway. Now, the things like water demand for washing machines and dishwashers, flow rates for taps and showers, and water demands for toilets. These are things that you can get from the manufacturer's literature. So you can compare different products and decide which one you want. Baths use a great deal of water. Even when you don't fill them very much, they use a great deal of water. Finding the volume of a bath is less easy than it should be. But if you were to be required to follow Part G, which is the part of the building regs that deals with water, then you would, you or somebody will have to do a calculation on water demand, water usage, and that will necessitate including the volume of the bath that you have installed. So you need to be able to find that out somehow. Next slide, please. Yeah, that's what I just said. You need the water efficiency calculations required by Part G. Now, Part G gives maximum values for water usage and flow rates. I'm not going to reproduce that here. What you need to know is that the building regs require water usage of less than 125 litres per person per day, which is calculated based on what fittings and fixtures you have and what appliances you have and how water efficient they are. That comes out of the water efficiency calculations. But local authorities are allowed to impose a limit of 110 litres per person per day as a condition of planning. And I happen to know that North Northamptonshire does impose that condition. So you need to figure out how to do the water efficiency calculations, or get somebody to do them for you, and plug in all the data from the appliances, fixtures, and fittings that you're installing, and they have to come out to less than either 125 or 110, depending on what is required. Next slide, please. Okay, water recycling. There are basically two forms of water reuse. Rainwater harvesting and grey water recycling. Next slide, please. And the simplest form of rainwater harvesting, I'm sure you've all seen these, is a rainwater butt. You attach it to a rainwater downpipe, and when it rains, the water comes out. And a rainwater butt has a tap on it of some description, like this one has right down at the bottom. You can use that water for non-potable purposes, such as watering your garden. Next slide, please. A more complex, higher volume rainwater system can provide non-potable water to the house. These systems consist of a very big tank, typically between 800 and 7,500 litres capacity, and they're usually buried near the house, but they don't have to be. There are above ground versions as well. You then get piping to take the water from the roof down to the house, and there are filters in the entrance to the tank which condition the water to a degree, and then you need to be able to pump that water out of the tank up to where you're going to use it. You can either pump directly to your washing machine or to your toilet, which is where you're able to use it. Remember, this water is not potable. Or you can pump it up into a feeder tank, typically in the loft, and then those the toilet and the washing machine can run off the feeder tank. Next slide, please. The wastewater from bath showers, washing machines, dishwashers, and sinks is referred to as grey water. As an aside, there is also something called black water, which is basically what you flush from your toilet. And there are black water plants that you can buy and install, but hardly anybody does. partly because that's yucky, and partly because they're quite expensive. So we'll stick with grey water. The thing about grey water is when it is treated, and I'll come to that in a moment, it's not safe to drink. You'll never get potable water by recycling. You have to take potable water from the mains. But you can use processed grey water, treated grey water, to flush toilets, wash clothes, and water plants. Next slide, please. There are several different ways of using grey water, ranging from the simple to the complex. Direct use is pretty much like a water butt. You basically just take the water from those things, your washing machine, your bath, shower, sinks, and you put it into a barrel, and you use it from the barrel much as you would use water from the water butt. Obviously that water has to be used pretty quickly because, as you know, that water will go foul from bacterial growth pretty quickly, particularly in summer. You can put that water on to gardens, but you wouldn't want to put it onto things like fruit trees or vegetable patches or whatever. There are systems much like the rainwater system, which use filters to treat the water. And you filter the water, pump it up into a tank, add chemicals, typically chlorine, to it, and that will kill the bacteria. And then you can use that water to flush the toilet. You could use it for washing machines. I would want to know how much chlorine was in that water before I used it in a washing machine. Then there are a couple of kinds of biological systems. One, if you have food debris, so you're siphoning off the kitchen sink, or possibly a dishwasher, basically what you need is a septic tank. There really isn't any other way to deal with it. A septic tank, and then the outflow from the septic tank goes through a sandbox, which is quite literally a box of sand. But sand is quite good at filtering. That water can then be used for toilets or watering gardens. And finally, and most people won't have room for this, is where you have grey water that doesn't have food debris in it, then you can use a reed bed. Reed beds take up a lot of space. They're basically ponds with plant life growing in them. So things like reeds and other typical pond-like growth. And you pump the grey water in, and nature does its stuff, and the water will eventually be treated. How useful is this? Well, about a third of household water is used for flushing a toilet. So if you can use reclaimed grey water to flush the toilet, then you're going to be saving a lot. Well, if you have a water meter, you're going to be saving a lot in your water bills. Next slide, please. All right, accessibility. Again, this is an issue of sustainability. We should be able to live in our homes our entire lives, but unfortunately, very few homes are actually accessible. Part M of the building regs deals with disabled access. It mostly deals with wheelchair accessibility. By accessibility, I don't just mean a level threshold to the front door and a toilet on the ground floor. A wheelchair user should be able to move around the building, which means wider circulation spaces, the ability to be able to turn to go through doors or turn around, so turning circle spaces. It also includes accessible vertical circulation, so a stair chair lift, like a standard lift, a stair wheelchair lift, which is also called an inclined platform lift. It's a platform that climbs stairs, basically, or a vertical platform lift or a full-blown safety lift. And a vertical platform lift looks a bit like a safety lift, but the mechanism is different. Obviously, these are all services and they need to be scheduled to fit in with other works for the same reason the building services need to be to fit in with other works to avoid scrap and rework. Next slide, please. All right, so cost, kind of important. Obviously, the cost will depend on the scope of the project. Done as a DIY project, most of your cost is going to be on materials and equipment, but some of that equipment will need expert installers, as in Dunley McCulloch's presentation. If you're going to put renewable energy, for example, in, you need someone certified to do that. Even things like heat pumps and so on, not really a handyman exercise. If the project is undertaken entirely by tradesmen, so maybe you instruct an architect who then tenders with a builder and so on, then obviously the cost is going to be much higher because you're paying labor costs. Next slide, please. What are the costs? Well, I remember reading before the pandemic a DIY enthusiast who claimed that he had done a reasonably deep thermal retrofit. A deep thermal retrofit is where you go to town insulating everything and making everything very airtight and so on. And he claimed he did that for £36,000. So almost no labor beyond his own free labor. What if you employ people? There was an item on the BBC website back in May reporting that Northampton Partnership Homes had was in the process of retrofitting 150 houses in Northampton, and they estimated the cost around £50,000 per house. Obviously, that was not DIY, that was entirely using tradesmen. What they were doing was super insulating the walls by putting about 180 millimeters of insulation in. They were adding high performance windows and doors. Obviously, brand new windows cost money. My house has, I think, 7 windows, front door and a back door. And they were topping up loft insulation to a thickness of 400 millimeters. The intention of this project was to reduce energy demand by half. Whether they did that or not, I don't know. Against that, before the pandemic, the view in the construction industry was that a deep retrofit, I mean, a really deep, approaching zero carbon retrofit, would cost around £100,000 per house. Next slide, please. Against that, and this is the funny bit, the Parliament's Climate Change Committee produced its 6th carbon budget recently, and in it, it proposed a programme of building improvements that, and I'll quote, balanced net zero pathway includes 3.1 million cavity walls insulated with 11 million lofts and 3.4 million solid walls, along with floor insulation, heating controls, and other measures. In total, 15 million households receive one of the main insulation measures, loft, wall, or floor, and a further 8 million benefit from draft roofing. All fuel poor homes receive a high efficiency upgrade. We assume all lofts and practical cavities can be insulated, but not all solid wall properties are insulated. And they gave an average cost of £8,600 per dwelling, and went on to say that 63% of homes spend no more than £1,000 on retrofitting energy efficient measures. I have absolutely no idea what they're talking about. I can't imagine what you can do for £1,000. You can't even put a boiler in for £1,000. So I don't know what their goal was it that they were simply intended to knock 50 quid off people's energy bills? I really don't know, but against the figures that I gave earlier, that doesn't seem realistic. Next slide, please. Right, last section is statutory approvals. Planning approval, listed building consent, if you live in a listed building, party wall notices or approval under the building regulations may be needed for a retrofit project. Anybody can apply for these, but you may feel that you would prefer an expert with experience, such as a planning consultant or an architect or a chartered surveyor, or even an installer. You may prefer to instruct them to make applications for and to negotiate your way through getting statutory approvals. If you want to negotiate planning approval in North Northamptonshire, I wish you luck. Next slide, please. Okay. Whoops. Yeah, that one. Bath and East Somerset Council recently published a really good document on retrofitting buildings, and it included this table, a table of retrofitting measures against consents that you may require, where LBC is not a radio station, it's listed building consent. BC is building control permission consent. PD is permitted development, and PP is planning permission. Where it has PD and PP together, even with permitted development, you still have to get that approved by the planners, but they ought to do that automatically. So putting in new glazing, if you live in a listed building, there will be strict controls on what you can do. UPVC windows won't be accepted. You'll need, in principle, building control consent, and you may need planning permission if it changes the appearance of the building. This is going by the book, by the way. I'm not saying that there aren't people who simply ignore this. So reinstating missing shutters, again, listed building consent. Putting shutters on a building that didn't have it in the first place might need planning permission because you're changing the appearance of the building. Cavity wall insulation, building consent, building control consent. Insulation, other kinds of insulation on the walls, and so on down the list. You can see that Bath being Bath, listed building consent is high in their mind, probably not so much in Wellingborough. But building control and planning permission is something that you do need to be aware of. And where you need to involve these building control and planning departments, it's best to get that before you start work, because what you don't want is to do a lot of work, spend a lot of money, and then have somebody come in and say, you can't do that, you have to undo it all. So instructing a building control person or seeking planning permission before starting work is a good idea. Next slide, please. Okay, so I started off by saying that the definition of a building is as a climate modifying enclosure. And so I leave you with the question, when the climate changes, do we change our buildings? And that's the last slide. Oh, there's one other thing. Marion did raise the question of what can you do DIY, and when do you need to instruct an architect or a tradesman or whatever. My view is, if you've understood anything since I said let's begin, then you might be able to do it as a DIY project. Otherwise, I suggest you talk to an architect. Any questions?
Thank you. Yeah, I just had a quick question for Greg, please. Could you give the reference to that beautiful matrix of the building services compatibility?
Yeah, hang on.
We will, all the slides will be put on the website, but obviously, as Greg said, he couldn't see it very well, so maybe the references are good.
Yeah. Hang on, I do have it. Yes. It's not a standard, it's a PAS, if you know what a PAS is. It's PAS 2035-2019. And the full title is Retrofitting Dwellings for Improved Energy
Yep, I got it.
Efficiency.
Thank you. Yeah. Thanks very much.
Okay.
I think Judy put a question on the chat, didn't you, Judy? Just before.
Yeah. Mm-hmm.
Would you like to say the question rather than?
Oh, all right. Okay. Yeah. What would be a realistic payback time for a £50,000 retrofit? And would it really be worthwhile? I mean, wouldn't it use up so much carbon as to be practically just not worth doing?
Yeah, I haven't really talked about embodied carbon, and that is an issue. And the answer is it depends what materials you use. Obviously, if you're going to go for wood fiber and cork and things like that, then there's not going to be a lot of embodied carbon. Is it viable? Well, I did work out that with that £50,000 refurb, the BBC report also quoted a resident who said she was saving a certain amount of money per month. I can't remember exactly. Marion, do you remember what it was? Marion's wandered off.
No, I don't remember.
Yeah, and I worked out that it would take 55 years to pay back if that was her saving.
Right.
Those prices obviously are before we hit £2,000 fuel bills, but
Yeah.
you know, the more expensive fuel, the more the payback makes, you know, the shorter the payback period. But I would also point out that the retrofit doesn't just save energy, it improves the indoor quality of the building. So you're not just buying cheaper energy supply, you're buying a better quality of life.
I see.
And you need to try and put a price on that.
Yeah. Thank you.
Thank you, Judy. John, you've got your hand up.
Hi, thank you very much. Greg, thanks for that. I wondered what you feel about the retrofit industry's ability to fulfill the demands on it, bearing in mind the housing stock is in such a parlous state.
Yeah, I think we're not in a good position. The construction industry is very short of people to start with, and even when it had lots of people, it had very few people who were competent to do this kind of work. Now, more people over time are becoming competent, but really, I think that you have to rely in part on certification schemes, and there are a few certification schemes around, but I don't know how many tradesmen have gone through that, and partly through finding somebody who's had a good experience with a builder. And if you have any contact with the construction industry, you'll know people who have a good experience with a builder, they recommend the builder, and then that builder turns out to be terrible. So it's difficult. I would say the best thing to do is to find the best tradesmen you can and stay on site and keep an eye on them, particularly when it comes to air tightness.
Right.
And in fact, in something like a passive house project, there is a person, full-time person concerned with air tightness. That's their job on site, is to do and maintain air tightness of the building. So yeah, it's a problem. I don't know the answer to it. I hope it'll get better.
Thank you very much.
Thank you very much for that question, John. I've got a question.
Mm-hmm.
So, I mean, listening you know, a lot of these workshops, you listen to what people are sharing and it's quite daunting, really. Some of them I'll walk away thinking, oh, I could go and do that now. But, so obviously that was what you were talking about. It's kind of a whole building retrofit to them.
That's what you asked me to talk about.
Yeah, of course. But I think obviously the cost and the timescale, etc., because I can imagine, you know, on our street, for example, that people will pick a couple of things that they think are going to have the most benefit. So it could be getting a bit of insulation and putting solar panels on the roof. So I wonder, obviously, when you're only going for part production, which some people may have to do, I'm not sure what the question is now. How?
What's the best thing to do?
Yeah.
Okay. The best thing to do
is it a good idea if you can't insulate just to get solar panels put on the roof instead, because at least that will help one way or another.
It will, but what are you going to use the solar panels for? You know, it's about using things in combination. Yes, you can use solar panels. You could stick the output, you know, feed it back into the grid, if anybody will pay you to do that, or feed it into a battery and just run your appliances off it, which would be something. But really, I would recommend the first thing you do is insulate to the extent that you can. I mean, if you can't do really high quality insulation for one reason or another, then do what you can. I think that's the best place to start. And airtightness, you know, and again, you know, without going full-blown airtightness, if you can at least seal up where obvious drafts are coming from, that would be a good thing to do too.
Thank you. Any other questions? I think Judy and then John.
Yeah, I was just wondering about air bricks, because you're talking about sort of sealing up all the cracks and different little sort of holes in the building, and I was sort of find that air bricks let in so much draft as to make it almost pointless sealing anything else up.
Yeah, I grew up in houses with air bricks. In winter, they're horrible.
Yeah.
I mean, air bricks can be used to satisfy that permanent ventilator thing that Part F. There's some real fresh air freaks behind Part F. You don't. If I had air bricks in a building, I'd seal them up. They're a bad idea unless the air brick is only on the outside and is there to ventilate a cavity, then or to ventilate the space underneath floorboards, for example, particularly as this Wellingborough, North Northamptonshire in general, is in a radon area, high radon area. So ventilating under the floor is kind of necessary. So, you know, if the air brick is not letting air into the building, then I would probably leave it be. If it's actually all the way through, which people used to do a long time ago, some very old houses may still have them, I would seal that up.
Right, okay, thank you.
And where's John? John, you had your hand up, and then Greg. Can't hear you, John.
No, I know. And stupidly, I've completely forgotten what I was going to ask. So we'll pass on that for the moment.
Right, thanks very much. And Greg?
I got my microphone on. Can you hear me?
Yeah, we can hear you.
That's good. Greg with double G, triple G. I wanted to just find out, I had some windows installed. They're double glazed PVC, and they're all very nice. But the one frame that was installed in my dining room is leaky. Now, I signed a piece of paper saying, oh yeah, everything's fine. But that was essentially on the day they installed it. But then 2 years later, or a season later, I noticed that, well, they've gone now, but the one window frame in the dining room is very leaky, and you notice it especially when it's windy. So how do I seal that up? Is there some sort of
it depends. Is this leaking around the edges of the frame, or
yeah,
okay? There are mastics that you can use.
yeah,
A bit like you seal, your bath, the edges of your bath and things like that.
yeah,
That there are mastics that, preferably a mastic that has a degree of elasticity, because things heat up and cool down, and so they stretch and squash and so on.
yeah.
But yeah, should be able to get that at B&Q. So
Oh, that's that easy.
It's not exotic.
Okay.
Yeah, I mean, I assume you've got white UPVC, and most mastics are white.
That's it. Yeah, UPVC. Yeah, that's it. Yeah.
Okay, thank you very much, Greg. And John, again, you might have
Yes,
remembered.
I've remembered now. Just going back to your question before the last two, you talked about insulation, and cavity wall insulation, from what I've heard, is a can of worms. Do you have a recommended type of insulation to go in there? Is it polystyrene or blown fiber, or?
Yeah, almost everybody uses blown the polystyrene beads. You can blow in cellulose, which, as I said, is recycled newspapers. But most people that's mostly used for loft insulation.
Right.
At an earlier webinar, somebody mentioned spray-on insulation. Yeah, that was actually in the list of insulants that I gave. It has a funny name, which I can't remember. There is that, but again, I just wonder how you would get it into the cavity. I mean, you'd have to poke the nose of the hose, whatever you use to spray
it around.
into the, yeah. And remember, there are all these wall ties holding the two leaves of masonry together. So you'd have to be skirting around all those to be able to install that gunk, which is probably why people use things like cellulose and polystyrene beads, because they're blowable.
Yeah. So ultimately, you're governed by who's doing what around.
Yeah, and as I pointed out, badly installed cavity, retrofitted cavity installation can cause problems. Doesn't mean to say it will, but it can cause problems.
Yeah.
If you're adding an extension or something, then obviously you have the opportunity to do your cavity installation as you build the wall.
Yeah, sure.
But if you're looking at retrofit of a cavity wall, then yeah, you're kind of limited to those.
Good. Thank you.
Thank you. Are there any more questions? So there is something that I'm pondering after this talk. Is I can't see where Greg's gone now. There you are, over there.
I haven't moved.
Obviously, we were maybe thinking about retrofitting one home, but when you talked about the number of properties at the beginning of the presentation, that millions and millions of properties that need retrofitting, and I think about the properties in Wellingborough, it sounds daunting just doing one home, let alone the thousands of properties in this town. Yeah. And how we might, so I suppose the question to all of us is how we might as a community enable some of this to happen, or as much of it as possible. Not that everybody needs to answer that question now, but it's worth, because often with these talks we can think about our own home, but our challenge is to help as many of us as possible to do this for lots of reasons. And maybe, they're the sorts of things that we need to be thinking about. I think that perhaps we can come up with collective solutions, then you can get economies of scale, as long as the work that is done to a good standard. And there has been obviously some, not large projects, but some housing associations that have done some retrofitting on properties, and not just recently, actually over the last 10 or 15 years. But, how do we help? Just especially when you're thinking about solar panels or power generation or whatever, the precursor is to put in as much insulation in the right places as possible, as you were saying, Greg. So yeah, I mean, that's the question for all of us, and I'm not just picking on you, Greg, from the council, but it's also for the council to think, how can it help our communities to do this sort of work? Stunned everybody into silence.
No, I agree. And I would add that in my view, we are going to affect the appearance of buildings, whether it's simply by putting external insulation on solid walls that are fair face brickwork, which changes the appearance of the building, or if we're also going to look at overheating, introduce things like shutters and sun shading devices and things like that, we're going to change the appearance of the building. And that is a planning issue. And at the moment, I would say planning departments, whether individual planners or not, but planning departments are decades behind times in what is necessary to do. They make it very difficult to change the appearance of a building. And that, you know, we're dealing with building physics. We're not dealing with opinions and cultural issues and so on. That, in my opinion, is one of the biggest problems. The other one is, as I think I've run past Marion in the past, if you really wanted to do a zero carbon retrofit of the existing building stock, and if you could do it for £36,000 per dwelling, which, you know, is going, it would cost £1 trillion, £1,000 billion to retrofit the UK housing stock. That's a lot of money.
Yeah, but when we, you know, for whatever people view, you know, with the furlough the other year, that was, and all the extra measures, I think that was well over £500 billion.
Was it? Okay.
Yeah. So, you know, we're actually talking about the other thing is you get benefits in that it will generate work for people.
Oh yeah, I'm all in favor of spending that trillion, but you know, I don't have the trillion to spend.
Well, we could get our machine out and start printing some. Lots of hands have gone up. John, do you want to go?
Yeah, I mean, just bearing in mind that we are looking maybe at higher temperatures, although that wasn't what I was thinking of originally. My thoughts were before we had the heat wave and those high temperatures. But surely, if the energy was cheap enough, surely it wouldn't matter if it leaked. I know it's slightly a weird thought.
Yeah, but that brings us back to nuclear energy will be too cheap to meter. You know, energy is expensive because it exists on the world market.
Yeah, but if it was on your roof,
if it was on your roof, then yeah.
And you had local generation and projects like that.
I did a quick calc for my roof. I live in a mid-terrace, late 19th century building. There just is not enough roof space to generate anywhere near the energy that I even included putting panels on the shed at the back, you know, in the hope that will work too. It just won't. There just is not enough roof space in my building to generate the power I use.
No, but I bet there is enough space on the Findon Road Industrial Estate and all the other estates around you. So if as a country we used every horizontal service as generation, I'm sure it would go a long way to creating enough energy.
I would pitch that against. I think every roof should be green for ecological reasons. So
yes.
We could compromise and have half, you know, the south facing half of the roof with panels and the north facing half of the roof with green. But yeah, again, design is a compromise.
Yeah, sure.
Could we compromise and put the solar panels on roofs rather than on fields? Then you can have green fields instead. Just a thought.
I wouldn't be against putting them on roofs, but just how much roof have we got?
Yeah.
So we've got three more questions, and then we will have to pack up. So I'll go with Jane first. She hasn't spoken for a while.
Yeah, sorry, this is probably not a question more than a comment, but I think obviously generation of electricity by renewable means has to go hand in hand with reducing the demand for electricity, because there's a real risk that if you just say energy is cheap to produce, that people's demands will just expand to use up what's available. That's all I wanted to say.
Yeah, thank you. And people may keep using lots of resources, because we might be using less resource to generate power if we're doing it ourselves, but it doesn't mean to say it stops all these various companies using up earth resources to make stuff that we don't necessarily need, really, in the scheme of things. So yeah. Then I say Harry and Greg as well.
Yeah, thanks, Marion. I just wanted to answer your question about how we're going to go about it, because Jane and I are from a family group in West Northamptonshire to yours, and we have a little program over the next 6 months looking at the 174,000 homes that we've got, wondering about precisely how to do it. And the idea that we've come up with is to, on a parish basis, recruit at the grassroots level and educate whoever would volunteer in that parish to be able to triage their community and identify the homes that really need some help, so that we can then build a hierarchy of need and understand better. The top-down approach that we've currently got just will never work. There aren't enough of anybody, either the money or the expertise, and we get sold stuff which is wholly inappropriate. So by looking at the grassroots, and we would really welcome your group coming along with us on that journey.
Yeah.
That's all I wanted to say. Thank you.
And I think in the longer term, the answer has to be that there has got to be government funding of some kind to support it, because a very small minority of people can afford to pay for everything themselves. They can do some of it, probably not all of it. But what we can do is to help people be mentally and in terms of their building kind of a little bit ready, because they've done the quick wins themselves that they can do, like stopping up the drafts and things like that. So you're kind of moving towards a position of being retrofit ready rather than actually saying, so at least people have got the information to hand when the funding does become available, which I hope it does.
Thank you very much, Jane. And then Greg, NNC Greg. Okay. There was something I was going to say, actually, to you, Greg, from North Northampton Council, to perhaps take back to your colleagues at the council. I mean, we really, we need to have further discussions with colleagues at the council about the things that we're discovering through our workshops. And one big thing really coming out of this conversation tonight is about planning policy, as well as interpretation of planning rules. And because if taking Harry and Jane's idea for that Climate Action West Northants is planning to do, with that team doing that triage in a village or in a parish, you'd want to be able to speak to a kindly planning policy person who would also be able to support that work around those developments in an area in any part of the county. So somehow taking that back, Greg, to North Northants Council, and obviously you're coming to a lot of our talks, etc., and hopefully you're picking up a lot of ideas, a lot of concerns that we have as well about how we move forward on this, not just individually, but collectively, because as people were saying, some people might be able to do some of this, all of this, or parts of this, but others would be in no position to do any of it. And so how do we help with that? And more than tokenism, and I don't mean that disparagingly to the council, it really needs to be, you know, because I know the councils try and move on money in relation to warm home schemes, funds from government, etc. But it's got to be what things could the council do that would really, really help. That might not actually be about money, but it might be about common sense, you know, particularly around planning stuff. And going on to the point that Greg, our presenter, made, you know, maybe we have got to do some retrofitting work that is going to change the appearances. So what are the most important planning rules in those situations? You know, if you were doing a village by village scheme, you know. Okay, so I think that's it now. That's 9:30. Unless anyone else has got anything burning to say, I just want to say a massive thank you to Greg Moore for doing this presentation for us today.
Thank you.
Thank you, Greg.
It's very mind-blowing, but I'm sure many of us will look at it again and look through different things. And I know if we start and do any of this work ourselves, those are the sorts of things we're going to have to look at and at least try and understand, even if we get someone else to do the work. So well done, and thank you very much, Greg. That's very kind of you to do.
Thanks so much.
Thank you. And the next session is 2 weeks' time on August the 11th, when Jonathan's going to be leading that, and we're going to be talking about food, sustainable food systems, and waste not, want not. So processes of waste, well, not wasting really. Anything else that anyone wants to say before we finish?
Thank you.
Yes, thanks for having me.
Thank you very much.
Thank
Thank you.
everybody,
Really,
and thank
really
you,
useful.
Greg.
Thank you. Bye.
Take care.
Bye-bye. Bye.
Bye.
Bye. God bless.
Bye.